Okay, so now that we know how to convert between our polar form and our a plus ib form, it is useful to do that because certain form is better for certain mathematical operation. For instance, if you do add or subtract, I'll just be lazy and go plus or minus. It's obviously easier to do it with the a plus ib form because you're a1 plus ib1 plus another number a1 plus a2 plus ib2. You can just add the real component and then the imaginary component separately. Now, of course, this is not nearly as obvious in the polar form, so what you would normally do is you would convert any polar form into your a plus ib form before you do any addition. Conversely, if you were to do multiplication and division or power, you would use a equals I theta form, because it's very simply, if you have a1 e to the I theta 1 times another number a2 e to the I theta 2, you just multiply their magnitudes together and then you add up the angles, because that's what you do when you have two things at the same base. Dividing is pretty much the same thing. You would do that. You would go a1, 2, 1 and 2. You would simply divide the magnitudes and subtract the angles. So to put in a slightly different way, if you have z equal z1 divided by z2, then the magnitude of z is the magnitude of z1 divided by the magnitude of z2, whereas the argument of z is equal to the argument of z1 minus the argument of z2. Power flows fairly obviously, so that's why you would choose to use the polar representation sometimes and the a plus ib convention sometimes, depending on if you're adding or subtracting or multiplying, dividing, or power. And so to round off our discussion of complex numbers, we're just going to have to cover a couple more things real quick. First, we're going to talk about, well, we know how to break down a complex exponential into cosine and sine, but knowing these, we can go the other way to express cosine and sine as combination of complex exponential, which would be useful when we deal with differentiation and integration sometimes, because e to the whatever is the easiest derivative we can get. So we combine it with this line. That's usually the trick. So you got cosine of negative theta plus I sine of negative theta. But knowing, of course, cosine of theta is equal to cosine of negative theta, being an even function, and then sine, it's an odd function, so sine of negative theta is negative sine theta. Using these, we can combine these to give us cosine of theta. You can get by adding the two lines. So we have 2 times cosine theta is equal to e I theta plus e to the minus I theta. So cosine theta is equal to e I theta plus e to the minus I theta divided by 2. So there you go. Similarly, sine theta has a very similar expression. This will squeeze over here. e to the I theta minus e to the negative I theta divided by 2I. And you get a chance to derive this yourself on the exercise. Okay, so lastly, we have to cover this one other thing called conjugate of a complex number. Strictly speaking, the definition of a conjugate is if you take any complex number and multiply it by its conjugate denoted by the star, it should give us a real number. To be specific, that real number should be the square of the magnitude of the complex number. In your a plus ib form, we want to make something that gets rid of the i's. You may or may not remember that we have to multiply by a minus ib. Demonstrating how that works. Because this one is fairly simple, we can just FOIL it into a square minus negative b square because of the I square. And so that's b square plus b square, which you probably do recognize is in fact the square of the magnitude of the complex number itself because of Pythagoras. So once again, that's forming the complex conjugate of a complex number in this form is to switch up the sign in front of your IB term, your imaginary part. And that's how you get the complex conjugate. For the polar form, or complex exponential form, is even easier because all we have to do is to get rid of this last part here. And what do we multiply to get that? Well, we multiply the same thing, but to the negative I theta. And we multiply this. We get rid of all the exponential because the 2 theta cancels out. And you have a square, which is in fact the magnitude square. And so there you go. That's how you form the complex conjugate for the polar form as well. So to conclude, let's bring back the statement that I put up at the beginning of the lecture. Here we have a complex exponential whose amplitude or magnitude is 1, and the theta here is minus pi. Well, let's sketch that out really quickly. On the complex plane, we have the real component here and the imaginary component here. Theta being negative pi, we go like that. And so your vector points this way, has a magnitude of 1. So therefore, e to the minus I theta is in fact negative 1. And of course, negative 1 plus 1 is equal to 0. So in fact, this statement is true, and now you know how to interpret it. And it actually relates all these mathematical constants with your positive, negative sign all together. And it's really quite neat.